North America, and I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter and panelists today. As you can see on the right side of your screen, you will see a control panel that looks similar to this one. You could submit questions at any time during the presentation by typing in the box highlighted in red, and I will read those questions out after the webinar during the Q&A segment. All webinar attendees are eligible to receive one NETA CTD and one PDH or 0.1 CEU just for attending today. You will receive this in an email within 2 to 3 business days of the webinar, and that email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again later or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during our Q&A session. Okay, our presenter today is Jason Sushak, Megger Cable Applications Engineer. Also joining us for the Q&A session at the end is Henning Ochen, Megger Product Manager of Cable Products. And, okay, let's go ahead and get started. Thank you for joining us today, Jason.
Thanks for having me, Jamie. I'd like to start out, jump right into this, and get going with the agenda that we'll go through with this webinar today. I will have a brief review of cable testing, why do we test, and a brief review of what very low frequency is. And then we'll go on to Vlf technologies, 10 delta technologies, and PD technologies, answer what each one of them is, what can we find with them, and what do the results tell us. After we discuss what the technologies are, we'll talk about creating a testing strategy and talk about the very next steps you can take. We'll start with the review section here. So of course, why do we bother to test? What's the reason that we test? And that of course is to increase the reliability of the system. And we can do that by reducing the number of outages with relation to the safety index. And we do that by proactively repairing and replacing questionable cables. There's two main types of maintenance that we do with cable testing. I consider the first one preventative maintenance, where we help ensure that no defects in workmanship or manufacturing enter the cable system. We catch those before the cable goes into service. And the other type would be predictive maintenance. After the cable's been in service for some time, we try to catch aging conditions before they fail in service. So, through normal aging, try to catch them before they're actually a real problem. So when I talk about aging conditions, pretty much what I'm talking about are water trees, although there are others. In a healthy cable, such as on the screen here, we have a radially symmetric voltage stress. No matter which direction you go from the center conductor to the outer conductor, the voltage stress is going to be uniform across the whole cable or any direction there. But when there's something like a water tree, it's going to distort the electrical field and create a region of very high voltage stress at the tip of the water tree. You can kind of think of this as a topographical map, and that's a much steeper hill to climb. But what happens that high voltage stress, eventually that converts to an electrical tree, and that electrical tree eventually fails the cable. So I know that these aren't the clearest pictures, I apologize, but give you somewhat of an overview of where the electrical trees and water trees might form in the cable here. This one forms out of the middle of the cable. And if we zoom in even farther, we can see that the electrical trees, they'll form at the tip of the water trees, and eventually they'll breach the entire distance of the insulation. This one's very close. It looks like it's breached all the way to the top, and it's about halfway to the bottom of the screen there for the electrical tree. Water trees can come in different shapes and sizes. I have here a picture of small distributed water trees. These are very common in the system. These aren't exactly not something we need to be super concerned about. They're in almost every cable. What we need to be concerned about, though, is when they become a critically sized water tree. That's when they become a problem. This water tree, as pictured here, would be in danger of failing at any time in service. It's breached enough of the insulation to create a very high voltage stress at the tip of that. And what you notice about the water trees is that they're a very dense construction. They're very dense and very straight. And when we compare that to an electrical tree, like we picture here, the electrical trees are much more branching, much more sparse. The other key difference here is that electrical trees, they have carbon deposited on the channel walls there. And the carbon, of course, is semiconductive, where the water trees, they don't have a carbon deposit. Now, of course, they're not a great insulator, but they're also not really conductive. So in 15 kV class cables, it's not impossible for a water tree to breach the entire insulation and not fail the cable. But if an electrical tree breaches the entire insulation, the cable will fail. So I have a couple of different examples here. We kind of break them up into local issues and global issues. So some of the local issues would be in splices and terminations here, typically workmanship problems, although sometimes it can be manufacturing defects as well. But basically those are single points that are an area of weakness. We can also have a local issue with a critically sized water tree, something that's at one particular point in the cable. And then we compare that to the global issues, these distributed water trees. That's something that we'll find throughout the entire length of the cable. The bulk insulation will have these water trees throughout either the entire length or at least a decent section of it. And these different aging conditions, these different weak spots in the cable, they need different methods of testing to try to locate them. So if we can take a look at this overview of the test selection, we can see that if we're looking for problems in the terminations, as on the left there, a partial discharge test is going to be the best choice of testing technology for that. But if we look closer to the right-hand side at the water trees, the tan delta test is going to be more effective at finding those. So we have to make sure that we try to pair the testing technology that we use to the type of issue that we're looking for. It's very important that we keep that in mind. So what is very low frequency? Fundamentally, it's a AC high pot that cycles at 0.1 hertz or one cycle every 10 seconds. And when we talk about our diagnostic tests, our tan delta and Vlf, our tan delta and partial discharge, the Vlf becomes the high voltage power source that we then add measurements to. There's three main Vlf testing technologies: Vlf withstand, Vlf tan delta, and Vlf partial discharge. And we'll talk about each of those in turn. There's also multiple different types of waveforms that we can use. Typically, there's three that we can choose from. We'll talk about this slide a little bit more later on, but just so you can have an idea going through, I find that it's a lot easier to show this visually than to try to describe it. So I have in the blue there 600 cycles of power frequency. I know you can't see the individual cycles because they're so tight together. There's also in the orange there 1 cycle of Vlf sinusoidal waveform. There's in the black 1 cycle of cosine rectangular, and at this zoom level it looks a lot like a square wave, but later on when we zoom in closer we'll see that that's not entirely accurate. And in the red there's one shot, we'll say, of damped AC, and you'll see that that's on the cable for a very short period of time. It's a very gentle test on the cable, and we'll talk about when you might use these later on. So for many, many years, we used DC test sets to test our cables. They ticked a lot of good boxes. They're small, light, portable, really, a lot of good things to say about them. But at the time, the cables that we were testing were paper leg cables or a laminated construction. Modern cables are an extruded construction. That's when we talk about XLPE or EPR cables, they're an extruded construction. And they behave differently than the laminated construction. There's an EPRI report, it's the numbers on the screen here. I believe that was published in December 1995, where they found that by applying a DC test to an extruded cable, those cables would develop trapped space charges, which would, in the end, reduce the cable life. So that's one reason why we don't use DC test sets anymore, especially on extruded cables. The other reason is there's research out there showing that DC testing is blind to certain defects in both types of cable, extruded and laminated cables. So it harms extruded cables and it can't find all your defects. So because of that, there's no IEEE standard for DC testing on extruded cables. In fact, IEEE 400.1 goes out of its way to specify that it's only applicable to laminated cables. So if we can't use DC testing, then what do we use? Well, obviously it's AC. We have a choice here. We can use 60 Hertz power frequency, or we can use 0.1 Hertz VLF. In an ideal world, I would choose 60 Hertz power frequency. However, it turns out that VLF has a huge power advantage over power frequency. Actually, VLF requires 600 times less power to charge up the cable, and this allows for practical field portable test sets. So I have an example of calculations here. This one we can see on the screen here, the formula is power equals 2 times pi times the frequency that we test at, times the capacitance of the cable, and there's some nominal capacitance per foot for every cable, times the voltage squared, and the voltage is determined by IEEE. So we cannot change the voltage. The capacitance is dependent on the length of the cable. 2 and pi are constants, so the only option we have here to change is the frequency. And if we take this 15 kV class cable, do a maintenance test on it, cable's 1,000 feet long, would need just under 10,000 watts of power just to charge a cable up if we do it at 60 Hertz. But if we do the test at VLF frequency, it takes less than 20 watts. So maybe I can go down to the local hardware store and buy a 10 kilowatt generator, but it's probably the biggest one they have on site. And that doesn't take into account any losses or anything. And again, this is only a 1,000-foot cable. If we look at a cable, 10,000 foot length, doing an acceptance test on it, same type of math there, it requires 166 kilowatts just to charge a cable if we do the test at 60 Hertz. If we do the test with VLF, it takes less than 300 watts, or 3 incandescent bulbs. So in the end, the difference we're looking at is something between a big box truck or even a semi truck versus something a couple of people can pick up. So that's the reason that we choose VLF for our testing purposes. When we make the connection here, for our VLF withstand test and Can Delta testing for products that have the Can Delta built into it, it's just a 3-wire connection. Very simple. It's the same way as we connect our thumpers and things like that. The first connection is always the case ground. That's the safety ground between the product and the ground rod in the cabinet there. The next connection is always a high voltage return that goes to the cable neutrals. And the last connection we make is to the high voltage lead going to the center conductor of the cable. Once the device is hooked up like this, we'll be able to apply a VLF withstand test or a Can Delta test. For partial discharge testing or for units that have an external Can Delta coupler, we need to include the coupler in the connection. So again, the case ground is always the first connection we make. We'll add a data connection to bring the data from the coupler back to the unit. Then we'll connect the high voltage return and the high voltage lead to the coupler. The last connections then will connect the coupler to the cable under test. And of course, same thing, we connect the high voltage return to the neutral wires and the high voltage lead to the conductor. So moving along to VLF testing, we'll talk about what it is, what we can find, and what the results tell us. So VLF would be like going to the doctor and saying, and he asks you to run on that treadmill for 60 minutes. If you make it to the end of that 60 minutes and you're in good shape, you pass the test. If you don't make it to the end of the 60 minutes, you fail the test. It's a go, no-go test. Very little in the way of subtleties between passing or failing the test. And the goal with this type of testing is to cause existing weak spots in the cable to fail during a controlled testing period. And this, of course, increases the reliability of the system. So the parameters for VLF testing, frequency is 0.1 Hertz. We can use sinusoidal or cosine rectangular waveforms. Voltage level would be acceptance testing, installation testing, or maintenance testing based on where we are in the lifetime of the cable. And the test time is 30 to 60 minutes by IEEE. And for more information on that type of what installation testing, acceptance testing, we have a webinar from, I guess, last year where we go into more depth on this. The frequency should be done at 0.1 Hertz. In fact, IEC requires 0.1 Hertz. IEEE allows you to reduce your frequency to as much as 0.01 Hertz although they highly recommend 0.1 hertz. If you do reduce the frequency, you have to increase the test time. So if I go to 0.01 hertz, I'm no longer doing an hour test, I'm doing a 10-hour test. For age cables, it's important to keep the VLF withstand test on the cable long enough to cause those weak spots to fail during your testing time. IEEE recommends 30 to 60 minutes of testing, but field results show that up to 25% of your faults can still occur in the second 30 minutes. This is for age cables. What happens is it takes a certain amount of time for those water trees to grow to the point where they can spawn electrical trees, and then those electrical trees also take some time to fail, to grow and breach the entire cable insulation. So the very worst thing we can do is start this process of failure and then remove our test voltage. That means that we left a weak spot on the cable that will eventually fail in service very quickly. So what can VLF detect? Pretty much water trees and electrical trees or other significant defects in the cable system. Workmanship issues in splices and terminations. Splices were made poorly. These are the type of things that it can find. VLF cannot tell you about the overall remaining quality of the insulation. Remember, it's just a go and no-go test. It can't tell you if the cable easily passed the test or if it just barely passed the test. VLF sinusoidal cannot tell you a leakage current, although cosine rectangular can. It measures a leakage current once per half cycle, and this would be pretty comparable to what you would get from a DC test if you're used to doing that kind of testing. And again, ultimately, this is a go and no-go test, ultimately a pass-fail test. So the results then, the cable can pass the test. In that case, it's held the prescribed voltage for the required time, and it has not broken down. Statistically, we find that that's about 97% reliable for the next 2 or more years. That's based on field results. If the cable doesn't pass, then the cable breaks down, and we now have a faulted cable. We need to repair or bypass that cable. That means that when we do this type of testing, we should have fault location equipment on standby, backup cables on standby, splicing splice kits on standby, things like that. If the cable does fail, we go out, repair the cable, and continue the test. We don't need to restart the test. But if the cable failed at 15 minutes in, we go and repair the cable, we start the test back up, and we hold the voltage on there for 45 more minutes. We don't need to restart from 0. So this would be an example of some test results from VLF testing. You can see on the picture there, it's just a constant sine wave over time. And in this case, the result, the test successfully finished. The cable held the voltage for the time applied and did not break down. For this example test here, we only held it on for 1 minute, but IEEE does require 30 to 60 minutes. If we held it on for any longer, the voltage waveform on the bottom gets a little bit too squished to see. Some other parameters here that we can look at. The test was done at 14.4 kV RMS at a frequency of 0.1 hertz, and the cable had a capacitance of 8 nanofarads. That's important to know because if the cable gets too long, the VLF test set will be unable to charge the cable up. 8 nanofarads is not very much, but if you get something into the microfarads range, it can be too much for the VLF unit to charge. So I've been talking about faults a bit here, and that might be a little bit off-putting to some people. You're saying, I'm going to put faults into your cable. Well, that's not the case. VLF only accelerates the aging conditions that are already existing in the cable. It causes them to fail during our scheduled testing time. And that's preferable to having that fail unexpectedly and in service. Is also, because of the power involved in a VLF test set, it's much lower than the power available from a substation, so your collateral damage is also a lot less too. It's very often that a VLF test would fail and you only have to splice 1 phase. Well, if it failed in service, you may have to splice all 3 phases because of the damage to the adjacent phases. So it's important to know then that VLF does not cause problems on the cable system. It only finds problems that are already existing. And NETRAC published these papers. There's the numbers on the screen here. And NETRAC says VLF has no adverse effects on cable life at prescribed levels. And I particularly like the quote at the bottom there. It seems reasonable to conclude that the current levels of voltage and time recommended by IEEE are reasonable at finding defects in a wide range of utility cable systems and do not pose an unreasonably high risk of failure for cable systems either during the test or afterwards. So if the withstand doesn't provide a lot of information about the insulation condition, what test do I need to run? And we have our choice here of Can Delta diagnostics for a global assessment or partial discharge diagnostics for a local assessment for, say, splices and terminations. And we'll talk about Can Delta next. So we'll go back to our doctor, and he's tired of people suddenly getting rushed off to the emergency room in his office there. So the next patient walks in, and he attaches a heart rate monitor to him. He says, okay, walk around for 5 minutes, and he watches the heart rate monitor. Okay, now jog for 5 minutes, and he watches the heart rate monitor. And finally run for 5 minutes, and he watches the heart rate monitor. At each of those steps, he can watch for signs of stress and gauge how easily the patient passed the test. It's also not a particularly stressful test. It's not a 1 hour run, it's a 5 minute run. It's nowhere near the stress levels involved in a withstand test. So what is Can Delta then? We use the Vlf technology as a power source, but then we add measurements to it. And this is a qualitative test that results in numbers that we can compare to the IEEE guide. And there's a test method that's prescribed in IEEE 400.2. We typically use Can Delta testing on aged cables, cables that have been in the ground for more than 5 years. If you want to use it on your new cables, go ahead, that's no problem, but it's typically used on aged cables. One of the more common uses I see for Can Delta is as part of a cable maintenance strategy. If we use the Can Delta consistently and go around through the system and test all our cables on a regular basis, we start to get an alert to critically aged cables. Even a single test, even just the first time we use the Can Delta test, can give us an alert to a critically aged cable before it fails in service. Of course, the more often we do this, the more trending data we have, the better we're able to predict things. And if we have that kind of trending data, we may get a year or two notice before that cable fails in service. The other common use I see for Can Delta is as part of a cable replacement project. I have $10 million worth of cable out there, but I only have $1 million to work with to replace it. How do I best use my money? We can use Can Delta to target the worst cables in the system and replace those first, thereby increasing the reliability the most for the least amount of money. Very commonly, cables are replaced based on age. Cables that have been in the ground for 30 years or something, they go to the top of the list. A lot of times they'll include fault history as well. This means that a lot of good cables can have been replaced. Cables that were perfectly fine are pulled out of the system, while cables that are in bad shape remain in the system. But with the Can Delta testing, we can go on a health-based system. We go out, test the cable, and say this cable's healthy and this cable's not, and we replace the ones that are not healthy. In this way, we can weed out the bad cables and replace them while leaving the good cables in and not wasting money on replacing good cables. So what is it able to detect? It can give you an estimate of the life left in the cable based on the bulk condition of the insulation. We can look for water trees, contaminants in the insulation, voids in the insulation. If we're using paper lead cables, it can detect things like oil leakage or dry spots in the cable, those type of things. However, it cannot tell us where the problem is, only that there is or is not a problem. It cannot tell us what specifically the problem is. Is it a void or a water tree? It only tells us that there is or is not a problem on the cable system. And it cannot distinguish between a major problem in a small section, think of that single large critically sized water tree I showed before, or minor problems in a large section. Think of those small distributed water trees I showed before. It's very possible that those result in the same number, And that's because of the averaging nature of the test. You have a long cable out there, anywhere from 100 feet to multiple thousands of feet, and in the end, you have 7 numbers to represent that entire length of the cable. There's not really enough information there to tell you where the problem is. The good news, though, is that a tan delta test is very hard to pass. If the cable passes a tan delta test, it's in good condition. It's very hard to get a false good reading. But if the cable doesn't pass the test, then you know that you have something out there that needs to be addressed. We just don't know what it is. And one of the other limitations of tan delta is it must be a single type of cable. Different characteristics of the different cable technologies, EPR and XLPE, will mask the defects in each other. So we cannot mix EPR and XLPE or XLPE and paper lead. It has to be one type of cable insulation. Now, it doesn't mean we can't do the test. It just means we can't compare our results to the IEEE charts. A lot of times what you'll have is 3 phases that are mixed very similarly. We can compare the 3 phases to each other, and if one is an outlier, then that's something we need to address. But we don't have the backing of the charts we find in the standard. So what are the parameters then for VLF testing? It has to be 0.1 hertz sinusoidal. That's the only choice we have if we're going to compare it to the IEEE charts. The voltage level is based on the rated voltage of the cable, and the test time is based on the number of points per measurement that we take. Overall, the entire test takes about 5 to 6 minutes, with voltage above operating voltage for only a minute or 2. It's a very quick, very gentle test. So test voltage is based on the rated voltage of the cable. This helps ensure the correct field strength across the insulation of the cable. One of the questions I do often get is, I have 15 kV class cables, but a 13.2 system. What voltage should I use? In a case like that, the difference is very small. I suggest using the rated voltage of the cable, the 15 kV. However, a lot of people have 25 kV class cables, but operate a 13.2 system, and that's a much bigger difference. If we wanted to test at the rated voltage of the 25 kV cable, it would be an excessive voltage. In a case like that, I would suggest going with the system voltage for your testing. But ultimately, they're your cables. They belong to you. That's something you'll have to have a discussion about internally. We can help you with that, but that's my recommendation. The tan delta test is done at 3 voltage steps: half rated line to ground voltage, rated line to ground voltage, and 1.5 times rated line to ground voltage. At each of these voltage levels, we take 6 to 10 measurements, and then we find the average value at each of these levels. We zip those 6 to 10 measurements down to a single average value. There's 3 criteria then to evaluate the cable. The mean tan delta, that's the average of those measurements taken at rated voltage. We zip those down to an average number and compare it directly to the IEEE chart. The differential tan delta, that's the subtraction of the half rated average from the 1.5 times rated average. Just zip those 2 numbers down to an average and subtract them, and take that result and compare it to the IEEE chart. And finally, the 3rd criteria then is stability, or called time stability in the standard. This is the standard deviation of those measurements for the rated voltage measurements. And what this means is how far away from the average a reading is likely to be found. So I have this example here of different aging conditions, and those of you with sharp eyes may have noticed that this chart goes out to 2.5 times rated voltage, where for the tan delta test, we actually stop at 1.5 times rated. That's just there so that we can see the effects at higher voltages. But what you see here is the red line across the bottom is a brand new cable, and you see that that's a perfectly flat line. When we do tan delta testing on new cables, this is the result we very much expect. We expect it to tell us our new cables are new. But as the cable ages more and more, that's where the tan delta test becomes more and more valuable. It tells us how severely aged that cable is. And you can see, especially with the dark blue line or the lighter blue line, that those tip-up numbers at 1.5 times rated voltage, they get much more severe as the cable gets more and more aged. So that subtraction number would become very large. There, of course, is a difference then at the rated voltage. number, but it's not as pronounced as the 1.5 times rated voltage. So I have example test here of tan delta testing. 3 phases were tested here, but we're only going to pull 1 out. And these are the 7 numbers you would need to do your manual calculations. And this is the average tan delta at F-rated, rated 1.5, the stability measurements for each of those, and the subtraction between the 1.5 times voltage and the half voltage. I'll reproduce that here on the next screen so we don't have to flip back. Here's a section of the IEEE standard. And what we do is we start going column by column. So the first column here is Vlf tan delta time stability measured by standard deviation at rated voltage. So the first thing we do is look at the stability measurement for the rated voltage measurement. And here we see it's 0.11. That is higher than the allowed 0.1, so it has to go into this row, further study advised. Moving across to the next column now is the differential tan delta measurement, which is the subtraction between the highest and the lowest reading, which is shown here. 1 minus 0.45 is 0.55. That is less than the 5 that were allowed, so this says no action required. And finally, we look at the mean Vlf tan delta. This is the average at rated voltage right here, and that's much less than the 35 were allowed. So we have 2 results here in the no action required category and 1 result in the further study advised category. Because of that 1 result, this cable becomes a further study advised. In that case, come back and test it next year, see how it's doing. No action required would mean it's probably good for the next 5 years, and action required would put that cable down for immediate replacement. So, tan delta, some of the things the results will tell us. If we have poor stability, that stability measurement number means something dynamic is happening in a static system, especially for extruded cables. That leads me to believe it could possibly be a partial discharge event going on. Something's changing in a system that shouldn't be changing. If we have a large tip-up, that subtraction number, that's an indication of more and more severe aging. More resistive current flows as we apply more voltage, so we get a higher and higher tan delta number. Or if the tan delta reading at rated voltage increases, that also indicates aging, but there's less of an effect there, as you can see from the chart, than the tip-up measurements. So tip-up is often the most telling tan delta result. Some of the advantages of tan delta, we get an assessment of the overall cable insulation. Gives us a number to represent the whole cable. It is a monitored test, so we get real-time results as we're doing the test. That detects water trees, voids, leakage, dry spots in cables, things like that. And because we have the charts now based on industry information feeding back into IEEE, we can gauge our cable's health based on those charts. It doesn't tell you where the defects are, and it can't tell you what the defect types are, but it can tell you that you have a problem out there. So moving along to partial discharge then, that'd be something closer to a doctor ordering an MRI scan for his patient. It's a very short, very gentle test. If the cable exhibits no signs of partial discharge, it passes the test. But if there's evidence of damage, then the cable fails the test. And the goal of partial discharge testing is to pinpoint where the problem is, possibly what the problem is immediately, take appropriate action for the problem you found, and you can do all that, but it does need a trained eye to interpret the results. The training requirements aren't severe, but there are some. So what is partial discharge? It's a low energy dielectric breakdown. In air, you know it as corona, but in insulation, you can't see it because it's not visible, but it's very much a similar phenomenon. It's an ionization of air that breaks down the voltage stress of the air or the void, but doesn't actually bridge 2 conductors. So it partially discharges between those 2 conductors. And it occurs when a voltage gradient is present, some difference between the edges of the void. So it really doesn't occur during DC testing. and it occurs in small areas in the insulation. So when do we use partial discharge testing? As a quality check for splices and terminations, as an acceptance test before the cable's initially put into service. We can also use it after work is performed on the cable. If you put a new splice in, we can do a partial discharge test to ensure that that splice was done well. It's also a very good test to do on an ongoing regular basis every 2 to 5 years, along with your 10 delta testing. That way we can get some trending data. We can also use it on cables that we suspect may be bad. Maybe it's been a troubled cable and we can find out more information about it, or we know that we've used a splice kit that we've had trouble with in the past and see if the splice kit on here is also in danger of failing. If PD is present, it contributes to a continued accelerated aging of the cable or joint, and eventually it creates a conductive path between the conductor and the shield. It's a continuously damaging process. If you have PD on the cable, it will only get worse. It does not heal itself. The damage to the insulation comes from enlarging existing voids, and that happens through a number of processes. When the area in the cable breaks down because of that high voltage stress, it releases high energy electrons and ions that attack the insulation material. It releases UV light, which again attacks the insulation, making it weaker. Ozone, high pressure, high temperature gases force the void to be a little bit bigger by expanding the air in there. All of these things contribute to a more and more damaged piece of cable that will eventually fail. So where does PD occur? Really, when we think about PD, we're thinking about defects in air voids. So it can occur in the bulk insulation. That would be a manufacturing defect, but it's not very common. The manufacturers are very good at making good cables these days. But if something like contaminants or impurities got into the insulation, or a void, an air bubble got in there, that would be an example of a manufacturing defect. Possibly too, if you exceed the bending radius of the cable during installation, when that cable's returned to being straight, you can have an air pocket in there, and that would display partial discharge as well. More commonly, though, we're looking at splices and terminations, places where people have touched the cable system. And it's very easy to make these mistakes. It doesn't take a lot to start partial discharge. Improper cutback distance, you're used to one manufacturer and you ran out of those splice kits, so you use the other manufacturer, and there's a 1/4 inch difference in there. It doesn't take a lot. Nicks and cuts, if the semiconducting peeling tool is set just a little bit too deep, you put nicks and cuts in the insulation, eventually that'll be a nice spiral partial discharge path there. Missing components, as we see here, there's some mastic tape missing. Misaligned accessories, I've seen this with pre-molded splices where the installer did not center the splice over the crimp body, and eventually that cable failed. So what can PD detect? Really local weak spots, voids, air gaps, defects. It can detect electrical trees, but there's not just one, but 3 asterisks next to that statement there, and that's because it's very unlikely that you'll find electrical trees. The reason being, they're only on the cable system for a short time before they fail the cable. So your chances of taking that cable out of service while that tree is there, but before it fails the cable, are pretty slim. So it will detect it if you're lucky enough to pull the cable out of service at the right time. Splices and terminations, again, same thing. Incomplete shrinking, that's a common one. A lot of times guys with heat shrink splices can get the top very well, but sometimes the bottom of the heat shrink is a little bit hard to get to, so it's not fully shrunk. Missing tape, improper cutbacks, things like that. According to IEEE, the partial discharge measurement can, at times, predict with a high level of confidence that a given cable is in very poor condition and is likely to fail in the near future. So what can partial discharge not detect? It cannot detect partial discharge events below the background noise. Oh, this is field testing. There's going to be some background noise. You're not in a Faraday cage. That is part of the measurement, is to measure the background noise, know where our threshold is, but if your PD events fall below that background noise, we're not able to detect it. We're not able to look for global insulation issues. Really what I mean by that is the small distributed water trees, because partial discharge does not detect water trees at all. Water trees don't have that flashing over characteristic. It's difficult to give a remaining lifetime assessment with partial discharge. There's certain red flags that we can say, but it's very difficult to say this cable is going to be good for the next year or 6 months or something. It's more of a threshold, this cable is in good shape or this cable is in bad shape. So IEEE says this technology cannot determine with complete confidence that a specific cable is in very good condition with essentially no probability of failure. I mean, that statement is talking about absolutes. Nothing's 100%, so that makes sense. It's the remaining life between the cables, between a very good and a very bad cable, that cannot be predicted with great accuracy. So trending, doing consistent every couple of years measurements where you get the trending data, that helps a lot with being able to predict cable remaining lifetime. So what are the basic steps then for doing a partial discharge test? You would start by applying the voltage in increasing steps. For example, half rated voltage, 0.8, rated voltage, 1.3 times rated, 1.5 times rated, 1.7, up to 2 times rated voltage. And we do that in a way, in logical progression, logical steps that allow us to find the partial discharge inception voltage. And that's just the voltage at which partial discharge starts. And typically for age cables, we like to go to 1.7 times rated. And for new cables, we like to go to 2 times rated. As you're increasing the voltage there, you'll come to a point where you need to create a map to locate your locate the point on the cable that the partial discharge is. And this can take anywhere from a few seconds to an hour to create this map. Partial discharges that will get worse, partial discharges that are more severe, are easier to detect and they require less time to map. I don't want to give a specific voltage for creating the map because if you have severe PD that happens at rated voltage, for example, that might be the best choice to do your mapping. But if your cable doesn't exhibit partial discharge until 1.7 times rated or twice rated, that would be a more appropriate voltage to run and get your mapping data. Optionally, we can do a partial discharge monitored withstand test. So if we remember back to the first section of this presentation, we talked about Vlf withstand testing, where we run the test for 30 to 60 minutes. We take those parameters, the 30 to 60 minutes, 0.1 hertz, and we apply that voltage again, but now we monitor it for partial discharge activity. That means our withstand test is no longer a blind go, no-go test, but it becomes a little bit more diagnostic as well. And this allows for two things. Number one, if we choose, we can stop the test at any time if we see too much PD activity. But more importantly, it gives us an additional acceptance criteria. So if we're running the withstand test, we may start seeing partial discharge near the end of the hour. And we say, this cable passed the withstand test, but because of this PD activity, I'm not comfortable putting it back in service. And we can take the appropriate action at that point. And that may be extending the Vlf withstand test more to cause that point to fail, or doing some more partial discharge investigation. Finally, we interpret the results and print the report. So by interpreting the results, what I mean is, what do we look for? One of the more important things that we look for with PD testing is a pattern of intensity and distance. So a high density of events indicates a problem. So if we look on that picture, the bottom half of that picture, it shows a whole bunch of clusters of dots there right in the middle there. That's a high density of events happening at the splice at about 100 meters away. The rest of the cable is in good shape. But partial discharge, cables that are in very good shape are very easy to detect with partial discharges. Points that are in very bad shape, as shown here, like this splice at 100 meters, are very easy to detect as well. Those points that are in between that we have to work on, that's a gray area. And that's the part that needs training. The other important piece of information that we get from this testing is partial discharge inception voltage and extinction voltage. The inception voltage is at what voltage do we start to see PD events? And that's very important because if we start seeing PD events below operating voltage, that's critical. That means that cable's seeing PD all the time. If the inception voltage is something higher than operating voltage, that becomes a little bit less critical because that means that cable only starts seeing PD during, say, transient switching voltages or lightning strikes or abnormal conditions. Equally important is at what voltage do we stop seeing PD events after we've started them happening? They're not usually the same voltage. So we run the voltage up, trigger some PD, and then start lowering it down and look for where we stop seeing the events. Similar logic applies. If that extinction voltage is below operating voltage, that's critical because a switching transient or a lightning strike can start PD, cable returns to operating voltage, and now it has PD on there all the time. If the extinction voltage is well above operating voltage, that's less critical because it only sees PD for abnormal conditions. There's many, many factors involved in interpreting the results, and in fact, it's probably a good topic for a webinar all on its own, but we'll do our best here to give you a basic overview. I pointed out the inception and extinction voltage in relation to operating voltage. That's very important. The event count, the more events that happen at a particular point suggest a more aged cable, a more severe partial discharge problem. The event intensity, a greater intensity suggests a more aged cable, a more severe problem. And we use the unit of picocoulombs to measure the intensity. Don't worry too much about picocoulombs. It's not a very intuitive unit to use, but one way to think about it is the number of electrons that were involved in the discharge. The more electrons, the more severe the discharge was, the higher this intensity measurement is. And as an advanced technique, not something we need to worry too much about, but if we look at the relative intensity of positive and negative polarity, so we have more events on a positive stroke of the voltage versus negative stroke, that can tell us some information about where radially in the cable the partial discharge is present. So for example, is it in the middle of the insulation somewhere? In that case, the positive and negative would be balanced. We'd have the same amount of events on both swings. Or is it the void on the semicon and insulation boundary on the outer side of the cable or on the inner side of the cable? And that will swing the polarity bias one way or the other. Long story short, in cables, any partial discharge is bad, but this will give you a little bit of information about what might be going on. A little bit of a visual representation of what I was talking about with the partial discharge inception and extinction voltage. If they're well above operating voltage, this is okay because we don't see PD there under normal conditions. But if they're well below operating voltage or even at operating voltage, much more concerning because that cable is going to have PD at all times. So I promise you we get back to this picture here, and I'm just going to start zooming in. You remember this is one cycle of Vlf sine, one damped AC shot, one cycle of cosine rectangular, and 600 cycles of power frequency. I'll start zooming in here. And when I get down to this level here of 3 cycles of power frequency, you can see that there's a huge difference, especially between Vlf sine and the rest of the waveforms. Power frequency, of course, is our reference, and that's the one that we strive for. And the cosine rectangular, the one in black, you'll see that for 1/2 of a cycle, it very closely mirrors your power frequency. So it oscillates from a negative peak to a positive peak, for example, in about the same amount of time as power frequency does. And damped AC is very similar to that as well, but it wrings itself out, it damps itself out very quickly. I'll admit to you guys, this is an ideal condition that I made in Excel. You're never going to see cosine rectangular be exactly 60 hertz, but it'll be in the same range. You're looking at a range of about 30 to 300 hertz or so, and that is dependent on the length of the cable. This is ideal, but it's very close to what you'd see. The one outlier here, though, is that VLF sign, and at this zoom level, it almost looks flat. It almost looks like DC. And in fact, where power frequency takes about 8 milliseconds to go from a positive to a negative peak, VLF sign takes 5,000 milliseconds, or 5 full seconds, to go from one peak to the other. So it's a much different rate of change of voltage compared to power frequency. And you do wind up, or you may wind up with differences in your partial discharge measurement. So we did this field test here. We took a piece of cable, same piece of cable. We tested it within about an hour of each other, VLF cosine rectangular, VLF sine, and damped AC. And these are the results here. With VLF sine, we detected this weak spot here at 950 meters at that splice, and it had a value of about 250 picocoulombs. Okay, excellent. When we came back and tested that same piece of cable, again, this is all within about an hour of each other, you can immediately see that there's a difference. We find that same weak spot at 950 meters, but there's also another one here at about 750 meters that VLF sine didn't detect at all. The other thing is the damped AC shows an intensity of 2,000 picocoulombs compared to the 250 of sinusoidal. Now that does not mean that damped AC is more or less severe on the cable. In fact, it's actually more gentle on the cable. It just means that it's better at triggering partial discharge. It's the same defect between sinusoidal and damped AC, just damped AC was able to get a bigger signal out of it, which means that background noise and things like that are much less of an issue. And we get similar results when we do that test with cosine rectangular. We get those same 2 points at 950 meters and 750 meters, but now we have a value of up to 4,000 picocoulomb. And that's pretty common because of that 5-second hold period on cosine rectangular. It kind of pre-charges the weak spots, and then when you switch, they have more energy to release in that discharge. And we can see the levels here related to sinusoidal and damped AC. So a little summary here of what we talked about with partial discharge, some of the important terms. All the waveforms that we talked about today, sinusoidal and cosine rectangular, and of course 60 hertz if you're going to use that, they're all continuous waveforms. The damped AC is considered a non-continuous waveform because you do a shot and then wait, interpret your results, and then you do another one. They're very separated from each other, whereas sinusoidal is a continuous waveform, same thing with cosine rectangular. Everything we've talked about today has been offline PD testing. That has a lot of advantages in that you can adjust the voltage that you're testing at, get some more diagnostic information, but online testing technologies exist as well with the limitation that you can really only test at rated voltage. We discussed inception and extinction voltage, and we discussed the PD pattern, level, and intensity. So when we talk about creating a testing strategy next, and there's really two approaches to this. The bottom-up voltage, which would be starting with the lowest voltage and working your way up. And this has a problem. There's a possibility to miss weak spots that form late in the test sequence. But you do have more opportunity to abort the test sequence. The other approach then is top-down. Start with the highest voltage and work down. In this, because we have a greater opportunity to catch weak spots that form late in the testing sequence, cables tend to be more reliable after this testing, but there's very little opportunity to abort the test sequence. Now, there's a big asterisk here. If the test sequence is aborted, the cable has not passed the test. I want to be very clear about that. The cable has not passed the test, but you may be able to place it back in service for a short time. When would you do this? Is if it's an inconvenient time or material or personnel are not readily available to repair it. It's an important cable, something like that. But it's important to know that cable has not passed the test and it may fail in service. You already know that that cable's got a weak spot on it. So my example for a bottom up here, I would start with an insulation resistance test, 5 kV or 10 kV IR test, just to make sure that that cable's in reasonable shape to start with. The next step up here would be 0.1 hertz tan delta test. And I like this because it works its way up in voltage. Half, rated 1.5. We're increasing the voltage with each step. The next measurement here, the next test would be a monitored withstand test, or it doesn't have to be monitored, but that's with your Vlf withstand test. We apply approximately 2 or 3 times rated voltage for the cable based on the IEEE 400.2 Table 3 charts. And this is our hour-long test. And finally, we finish with a PD test, preferably damped AC, up to 1.7 times rated voltage for age cables or twice rated for new cables. That way, if any of those weak spots show themselves late in the monitored withstand test, we have an opportunity here to catch them as well. Getting ahead of myself here. With the top-down example, I would still start with the insulation resistance test, 5 kV or so, just to make sure that cable's in decent shape to start. Then you would start with the monitored withstand test. You come out there and hit it with your highest voltage just to start. That way you start the aging conditions to failure process, and if they should fail late in that hour test, you have additional opportunities to catch them later on. Next step would be a tan delta test, and keep in mind that water trees can grow during tan delta test. And finally, finish off with a partial discharge diagnostic test. That way, if there are any weak spots that came up late in the testing, we have a chance to find them. So coming back to our test selection here, this is from the beginning of the slide here. Makes a little bit more sense, I think, of why we would choose different tests to look for different things. So there's no one silver bullet, there's no one answer to match everything. We have to keep in mind what we're looking for and how we want to approach the problem. Are we looking for water trees? Are we looking for workmanship issues in joints and terminations? Are we looking for global issues in the whole cable insulation? I have a side-by-side comparison here of withstand testing, tan delta, and partial discharge testing. I'm going to skip this. I see we're running a little bit out of time here, so you guys can take a look at that when you get the slides yourselves. So what are the next steps? So the first steps you have to take then are decide what tests are appropriate. What are your areas of concern? Water trees, workmanship issues. Take a look at that slide that I just showed and make that decision and come to that conclusion first so that we can make that targeted plan. Next, we have to decide what age are the cables, and this may factor into the area of concern as well. But new cables don't have any aging condition on them. They're new by definition, so we're not really looking for distributed water trees. So there's no need to do to do tan delta testing, for example. So the age of the cables will affect the types of tests we want to do as well. Is there a particular project you have in mind? Is there a cable replacement project where I have $10 million of cable and only $1 million to replace them, and I want to spend my money the best? That's going to affect the type of equipment we get as well. Or is there a new project that we're looking for to verify, to do acceptance testing on? After we decide what we want to find, then we need to put together a test plan, either the top-down or the bottom-up example, or something that works better for you guys from your own utility. One thing people tend to neglect or don't think about is the personnel. Who's going to run the test? Who's going to interpret the results? Who's going to receive the training to do these tests? And from a technology standpoint, where will the data be stored? Are you going to store it on the test equipment itself, paper PDF reports on a database somewhere? These are all options that you have to consider. And finally, with all this in mind, we have to determine what kind of equipment we need to get. What is important is what voltage class are the cables. Higher voltage class means a bigger piece of equipment. What installation are the cables? What's the human-machine interface like? Is it easy to use? Is it easy to train on? Easy to get people to operate the equipment? So we do have some examples here of equipment that we can help you with. Our Vlf 34 is a small portable sinusoidal Vlf unit. has an external tan delta available for it. Vlf 45, a little bit bigger unit, a little bit higher voltage, goes up to 45 kV. Sinusoidal with a built-in tan delta. We mentioned a little bit today that if you're testing, you can expect to have faults because you're finding those weak spots. So we have some fault locating equipment as well. Anything from these small portable easy thumps. This is about a 70-pound box. Great for 15 kV class cables. Our smart thump would be the next size up from that. Nice big wheels on it, great for up to 25 kV cables. If those aren't big enough, now we're going to start looking at vehicle-mounted equipment. Something like our TDM 45. I like this unit a lot because it does everything we talked about today. It does damped AC, cosine rectangular, and sinusoidal all in one box, which means we can do partial discharge testing at power frequencies and tan delta testing with 0.1 hertz. If that's not enough voltage, we have this vehicle mount Vlf 54, and now we have some bigger fault locating equipment like our SFX 40. This one goes up to 40 kV. It is a portable version, as I show here, but more commonly it's vehicle mounted. Something like this, our SWG, nice big thumper, goes up to 32 kV with up to 3,500 joules. And if that's not enough, we have our integrated test band system, something like our Centrix 2.0 here, completely integrated, lots of safety interlocks, highly customizable. Something like our Centrix City here, which takes the TDM 45 and the SFX 40 from the previous slide, puts them together in a van, adds some safety interlocks, integrates everything together, and both of these systems come back to a single point of control, just like both of these, just like shown here. One joystick controls the entire unit. So if there's anything you'd like some more information about, ask us for a demo, ask us for a quote. In the survey after the webinar, there's a checkbox if you want us to contact you, or you can get in touch with us with your local sales engineer through our website or give us a call. So thank you very much for listening. Jamie has a couple of closing remarks here, and then I think we'll open it up for some questions.
All right, thank you very much, Jason. At this time, the presentation portion of the webinar is officially concluded. Before we get started with some of your questions, I'd like to make you all aware of another very informative upcoming cable webinar titled Cable Safety, Switching, Cleaning, and Installing, that will be presented by Mark Franks, Senior Cable Instructor at AVO Training Institute. And that's going to be next month on Tuesday, September 19th from 1 to 2 p.m. Central Standard Time. But Mark is very knowledgeable cable professional, and we definitely recommend checking out that webinar as well. I've included a registration link for that webinar in the PowerPoint presentation that will be emailed to all of you next week. Okay, let's take about 30 minutes to go ahead and do a Q&A and answer as many questions of yours as possible. For those that are leaving, when you close the webinar window, a survey should pop up on the screen. We'd really appreciate it if you could take a couple minutes to provide your feedback so we can continue improving upon future webinars. Also, a copy of the presentation, as well as a link to the video recording of the webinar will be emailed to everyone next week, so be on the lookout for that. And you could also view previous webinar recordings as well as upcoming webinar schedule on our website at us.megger.com/webinars. All right, now let's go ahead and get to some of your questions. Okay, first question we have is for going to be for Henning, our panelist, and that question is for which defaults is DC testing blind?
Okay, typically you can say DC testing finds resistive type defects fairly well, but not defects that are more capacitive type defects like you would find in splices and terminations. And the difference in, let's say, voltage you would need to find one versus the other one, you know, we had some experience with some customers where we found where a 10 kV AC test or Vlf test would find a defect and would shut the set down, where it would still work at 25 kV DC and would not fail. So the differences can be very significant between the type of defect, and that's why when we look at splices and terminations, the Vlf test is typically considered the much more forthcoming test compared to a DC hypo test.
Okay.
Maybe also one other quick comment on it. By the way, the voltage levels you need for DC testing are substantially higher than for AC testing or Vlf testing. IEEE on DC testing typically on new cables 5 per unit, where you have on Vlf testing at the max 3 per unit. So there's a big difference also in the applied voltage, which again, the lower the test voltage you can do, the better it is typically for the cable.
Okay. Thank you, Henning. Next question is for Jason. For failed cables, what is the minimum length that is required to analyze the failure?
So I'll answer this based on the individual tests that we talked about. For Vlf withstand testing, I can test as small as you can make them. Any cable that you can put 2 terminations on and have something between, Vlf withstand testing can test it. Practical length, really, 30 feet. I don't think too many people have something much shorter than that. Very similar for tan delta testing. You can test very short cables, 30 feet. Probably most people aren't going to bother testing for cables less than about 100 feet now. For partial discharge, though, there requires a little bit of space there for us to get that mapping data. And I would say for a minimum, you're probably looking at a minimum of 100 feet. Really probably closer to 200 before you can really start getting that mapping data. However, I can still get partial discharge results. I can say, hey, this cable has PD or it doesn't, even on very short cables. It's just I won't get that mapping information. I hope that answers the question.
Okay. Thank you, Jason.
Henning, do you have anything to add to that?
Yeah, there's maybe in terms of the tan delta testing, you need, and I don't know exactly the number, but it's in the few nanofarad that you must have minimum cable capacitance in order to measure tan delta. So it's not microfarad. You don't need microfarads, but you need something in the nanofarad area. I think maybe 8, 10 nanofarads. It's specified by, different manufacturers have slightly different levels there. As a minimum length or the minimum capacitance, which translates into a length of a cable in order to do, tan delta testing.
Okay, thank you, Jason and Henning. Next question. This one is going to be for Henning. If a cable is already faulted, like splice failure, for example, how long would you have to VLF before verifying the fail on that span of cable?
Well, if the cable is already faulted, you cannot do any type test that we talked about because you cannot charge the cable anymore, right? So, a failed cable, you cannot do any type of withstand test or diagnostic testing on it.
Okay. Can I just add? After you repair the cable, put a splice in, you just pick up where you left off with the Vlf testing. So if it failed 20 minutes into your test, you repair the cable and then pick up and do 40 more minutes. But you have to repair the problem first.
Maybe that's absolutely sure. You need to fix it first, and I think you mentioned that you only add the balance of the time to it. You don't start from ground zero again, because the whole idea is for Vlf withstand testing that you get, especially on an old cable, service age cable, you get a time of 60 minutes. And now we didn't show you the chart here why 60 minutes is important, but Jason alluded to it because there is a certain time it takes to convert the water tree to electrical tree, and then the electrical tree must have a certain amount of time to be able to grow to failure. And that's really why on service age cable, it's a good practice to test for 60 minutes to make sure that basically everything that was converted to electrical tree has enough time grow through the insulation. And if you look at the growth rates, which are about 10 millimeter per hour, and you look at the typical insulation thicknesses for medium voltage cable, then you can see why an hour period is a good time to accomplish this.
And there's some more information about this in our previous webinar about Vlf testing.
All right, next question is for Jason. What is the standard value of tan delta?
Okay, there's no specific standard value. That's why we have the IEEE charts, so that you can go and reference them. I'll tell you though that typically your magnitude of them is going to be 1 to 2 or 3 times 10 to the -3rd radian. It's kind of an awkward unit, but when we talk about the angle that's involved there, it's very similar to power factor testing. If we scale that up to the size of the Earth is about 25,000 miles around the circumference at the equator. We would be looking at a distance of about 12 miles along the surface. So it's 12 parts per 25,000 ballpark. Or that works out to about 1 to 2 or 3 times 10 to the -3rd radians. But yeah, there's no specific one or the other. You have to go to the chart, and it varies based on the cable insulation as well. Paper lead has a particular set of numbers with the chart. EPR has a particular set of numbers. EPR even has a particular set of numbers based on, let's say, the color. Black EPR has a color, pink EPR has a color, white has a number as well, and XLPE has a different number. So there's no one standard number.
All right, thank you, Jason. Next question is for Henning. If the cable is long, the capacitance increases. Here, according to you, VLF can't be used. Then what should I do?
Well, you cannot say VLF cannot be used. The best way to approach this problem is to do a quick calculation of the cable capacitance, and then compare that number to the test capability of your test equipment. Typically, you can say, the sinusoidal units have overall a much smaller test capacitance than the cosine rectangular units do have. So if you're using a sinusoidal unit for withstand testing, you have the option under IEEE, at least, you can drop the frequency, which changes not only the test time you really need. Unfortunately, it also obviously changes the stress you put on the cable, because your change of voltage over time is even much more extended. So it's not only that you need the same amount of cycles by going to 10 times the length of the test time or duration, but you also changing the stress. So it's not advisable. That's the only thing you can do really on sinusoidal test set. Or if you really have long cables, and typically the cosine rectangular technology is the preferred technology, because you can go, typically you have a test capacitance maybe of between, let's say, 4 or 5 microfarads, where on a typical sinusoidal unit you have maybe 1 microfarad. And so if you have long cables that have really high capacitance, the cosine rectangular might be the better choice. Okay. Because you can keep it there. Cosine rectangular is only always 0.1 hertz. It's never at a lower frequency. Okay. And we make units. This has nothing to do with what the products really, but we can go up to, for one particular customer, to 25 microfarad at 60 kV RMS. So if you wanted to do that test set in a sinusoidal unit, it would be a very huge test set. It would be technically very, very complicated to do, and questionable whether you would be very successful. Okay. Because a big difference is, in a sinusoidal, you must create the charging energy within basically 2.5 seconds, and you must dissipate the same energy you just pumped in. You must dissipate it, and that's why sinusoidal units run very hot. And obviously, the more energy you have to pump in, the more of the problem the heat taking the heat out becomes. The cosine rectangular work on a resonant principle where I don't have to recreate every quarter cycle 100% of the energy I need to charge a cable. I might only need about 10% to create. The other 90% I can recover, and that's why the cosine rectangular technology is more suitable for really long cables with large cable capacitance.
All right, thank you, Henning. Next question is for Jason. The connections for tan delta were not shown in your presentation. What does the measurement 6 to 10 points mean, and what type of connections would be used?
Okay. The connections for the tan delta are the same as the 3-wire connections for internal. When the tan delta is built into the unit itself, it's just a 3-wire connection. There's nothing extra you have to do. Some units, though, have an external coupler, and it'll be very much the same here. I chose to use a partial discharge coupler. Otherwise, the sides get too complicated. But it's very much the same. We have to bring the high voltage lead through the coupler and out to the cable, and also bring a data connection and the high voltage returns as well. But the connection is very similar to that. It depends on if your device has the tan delta built inside, like this one, or if you need to use a coupler. To the other question here, what does the measurement 6 to 10 points mean, and what type of connection? So the connections are as described here. The 6 to 10 points, like I show here, we do one measurement every 10 seconds, or one measurement every cycle. It's the same. And we hold that voltage there for 6 to 10 cycles. At each cycle, we take the measurement. We do that to get that stability measurement, really. If you took just a single point, you can't make a stability assessment off of it. But if you took multiple points, like I show here, you can see if they're stable. If you have 6 points that all come back to be the same value or very, very close, you have very good stability. If there's range there, then you have more and more poor stability. And we just simply take those measurements then and zip them down to an average. And we work with the averages as we do the assessments, really. It's just a matter of holding the voltage at that level long enough to measure 6 times, to measure once per cycle.
All right, thank you, Jason. Next question is for Henning. How do the operating temperature and loading variation influence the degradation of cable insulation?
Okay, it's basically coming down to the temperature or loading. Typically, loading equates to temperature because I have more load on it, I have more resistance, so I get at a higher temperature. And the aging of cables, these aging processes that we have in the cable are basically chemical reactions that change the polymeric material, or that change the paper. When I have paper cables, oil insulated cables. So you can typically say that for every 10 degrees in change in ambient temperature, the reaction will double its speed. So the hotter it gets, the kinetics of the chemical reactions, they increase very fast. So that's why the temperature is certainly one of the fundamental aging parameters you have that affect the insulation, and you might also have a combination of temperature but also mechanical, because as you well aware of, if you have a lot of changing temperature from changes in loads, you get also, let's say, thermal expansion and contraction. So you have also now the mechanical aspect of aging. And so sometimes you have, some cables are not always all the way buried. They might run in cable trays above ground somewhere. You have UV radiation from the sun, and you have obviously those cables see the UV during the day, and they have much more temperature change from day to night than a direct buried cable. So basically all these factors together in a given circuit will affect the aging of that insulation system. But temperature is obviously one of the very fundamental ones, and the higher the temperature, the faster the aging will go. Okay.
All right, thank you, Henning. Next question, this one's for Jason. When performing offline PD testing, do you have issues with cable attenuation?
Yes, of course we do. Just like with TDRs or anything, transient waves like that, the losses in the cable and the capacitive filter effect, we'll say, of the cable definitely do attenuate out the signals. Generally speaking, we can go, depends on the cable. I mean, it's hard to pin a number down, but maybe about 5 miles with a single coupler. If it gets much longer than that, or even at that point, you have to measure from both ends. And even then, there is a limit to that. You might get probably not double that length, but somewhere 7-8 miles, even if you measure from both ends. There is a practical limit to the length of the cables that we can measure because of the attenuation effect.
I might want to add to it, this is not only in offline PD testing, this is obviously also a problem for online PD testing, and sometimes even a bigger problem, because the signal you can create for online is limited by the voltage, by the operating voltage. And unless you have maybe access to, if you have a manhole system where you can actually put PD detectors, let's say, in each manhole, so you have a fairly short distance, maybe 400 or 500 feet between manholes, then it's fine. Now, if you don't have access because you don't have a manhole system, then on online PD testing, you have very much the same or worse condition, like I said, because the voltage level is limited. So attenuation is, whenever I have a pulse traveling on a piece of cable, I have to deal with that issue. So it's not just limited to the offline PD testing.
All right, thank you, Jason and Henning. Next question is for Henning. TG delta is also very useful for a fingerprint on new cables. Do you have any experience with this?
Well, you know, in my opinion, fingerprinting a new cable, if you want to use 10 delta will not be a good tool to do that. I think Jason alluded to it, because 10 delta is a measure for the aging condition of the cable. Now, a brand new cable shouldn't have any aging condition in it. So 10 delta, you're not gonna get any result. You might even get a wrong result, because a brand new extruded cable, especially when we talk about extruded cables here, they have some byproducts from the manufacturing process, and they can affect the dielectric properties in a way that it shows you maybe a higher 10 delta than you really have. That's why the basic rule is you don't want to do any 10 delta testing, or for that matter, dielectric testing on cables, if you before maybe a year where they have been in service and under load, because you start burning some of these components off, and then you get a true 10 delta reading. So for fingerprinting, it would be not a good tool. Fingerprinting, you could use obviously PD testing for fingerprinting, so to speak, on your splices and terminations to see how well that is. Assuming it's very minute, so you say I can leave it go for the next 5 years. The other fingerprinting that comes to mind is a more mechanical one, to really have a good idea where the splices are. I mean, you might have maps, but you could also run a TDR test to see where your splices are, so you have a basic information about where splices is, which might be helpful down the road. Whenever you have to do fault locating, it's nice to know where the splices are in the cable. Or when you do later on PD testing, it's also very nice to know where the splices are, okay? Even you have ways to determine where the splices are, but I'm just saying, whatever you can do up front to define the cable might be helpful over the life of the cable, which could be, 40, 50 years, right?
Yeah, okay. I agree with Henning on that. Exactly, Can delta testing on new cables, it's not going to hurt anything necessarily, but what kind of information do you get from it? Wait till you come out and do your first maintenance, scheduled maintenance on it, a year or even 5 years out, and that can be your baseline then. 5 years of aging on a cable is not going to be too much. 99.99% of the time you're going to be almost new, and that can be your baseline. But a partial discharge testing when it's brand new, very useful. The TDR is the type of thing that you might want to keep records on. So, yeah.
Maybe one other comment on this, because the question comes up sometimes. People say, well, can 10 delta give me also some idea about the condition of the splices? And I just want to relate maybe some of the experience back from the ICC, where this was discussed in much detail. And so far, it is very hard to come up to draw any conclusions from 10 delta measurements to relate to the condition of the splices. And that's why right now you won't see it in any of the IEEE standards. That issue is not addressed, because there isn't, so far we have not found, or nobody has found, any correlation there. And again, if you are interested in the splice condition, PD is a tool of choice. There's no question about it. That's really the strength of PD measurement, is any type of, let's say, layered dielectric materials you have, like you have in termination and splices. The PD is absolutely the best tool to show not only that you have a problem, but also how bad of a problem you have. It's very quantitative and qualitative measurement, and you get a location. So that's a home run.
All right, thank you guys. Looks like we have time for about one more question. This last one's for Jason. If during Can delta 10 measurements for taking the average, we have some 1 to 2 measurements with big deviations compared with the average, what might be the reason for this?
So as Henning was just talking about, trying to make any kind of assessment off of a Can delta measurement is very difficult. Something like this, my best guess would be you have some kind of partial discharge going on. You have a weak spot, a void in there, probably a void that's building up a charge, and then it discharges right at the same time that your unit is making the measurement, and that's going to increase the current flow through it. Something like that. You have something dynamic going on in a static system, and whatever the case might be, that's no good. So that's the reason, actually, you hit specifically on the reason why that stability measurement is in the standard at all, is if we have these I'm sorry, I'm drawing a blank on the word, these exceptions to the measurement, that's something that needs to be investigated a little bit more and figure out what's going on. And the investigation may be as easy as just running your VLF test for an hour, and if something fails, well, then you found your problem. Partial discharge test may be appropriate as well. If that's the thing that is causing the problem, PD is likely to find it. So it's very difficult to make a specific, this is your problem thing, but those are the type of things I would look for. I don't know if Henning has any other experience on that?
Well, the only thing I would say is if you get if you see on one reading or on one test, on one phase, you see this, to me it would be interesting to see at what voltage level it occurs. Does it seem to be, at the higher voltage level or the lower voltage level? And if I might just rerun the test on that one phase just to see, is this something that's always there, or was it just a fluke? Because, sometimes you get a fluke reading, okay? I mean, it's all statistics, okay? So but if I see the same pattern 2 times, normally that's what it is, and I still might have an explanation, okay? That's one thing about cable testing. We try to explain everything, but there are some things that, unless, stopping short of cutting the cable out and looking at it, you might not be able to diagnose it. It's like, any diagnostic test is different. The go, no-go withstand test is either good or bad, But on a diagnostic test, there might be some situations where, unfortunately, nobody can really interpret that test. But those are very, very limited cases. Typically, it's fairly easy to interpret all the stuff that you see there. So,
I might just add, with relation to tan delta, is if the tan delta test comes back good, it's a very, very sensitive test. So if it says your cable's good, the cable's probably good. But if your tan delta test comes back bad, it says your cable's in bad condition, I wouldn't necessarily blindly follow that. I would take a minute and say, is there a splice that's maybe a problem? Or one of the few things that we can do relatively easily to address this is replace the terminations. You know, clean them up or replace them. It could just be as easy as dust over the terminations and you're leaking current over that. So those type of things. If your tan delta test comes back bad, don't automatically jump to replacing the cable. Take a look and see if there's something you can do to improve those numbers before replacing the cable.
Well, that's a good point, because especially if there's a maybe three-phase circuit, it's fairly long, several thousand feet, and you see a delta 10 delta, an increase in delta 10 delta when you go from maybe from 1 U-naught to 1.5 U-naught. This is always the first thing you want to do. You want to redo the terminations and run another test, because, like Jason was saying, leakage over the termination, over bad termination, it has been, because the termination sits normally is exposed to the let's say to the outdoor environment, right? So it sees a lot of aging that the cable itself underground doesn't see. Has the UV issue and all these things. So it's a good thing to look at that first, because it's fairly inexpensive to do that compared to putting a new circuit in, and that has been proven by quite a number of utilities. They will do that step first before they go any further, and then be tested, and then look at that again. Okay. The only other thing is, when you have a good 10 delta reading, okay, or let's say a 10 delta reading that's within the norm, okay, it means really, I hate to say, the cable is a good or bad cable, because it only tells you that the dielectric aging condition of that insulation is still very, very, very tolerable, very, very okay. That doesn't mean you could not have one spot in there, like Jason was showing there. You might have one bad water tree and that's going to blow, right? That's why, after doing a 10 delta test to get the global condition of that cable on a service age cable, you typically, if you're really looking for reliability, you want to do also one other test to find out whether you have a local issue, because the 10 delta will not show you the local issue, okay? It can only show you the global aging condition. So if you had a fully grown water tree that I think Jason was referring to, one of those water trees that has almost crossed the entire insulation, it just takes one voltage spike and the cable will blow. So the 10 delta will not show you that one spot, okay? So it's always a good practice to do that. And in the end, it comes all down to what Jason said at the end. What is your plan? Why you do testing? You do it because of cable replacement. Then you're typically only interested in the aging condition. If you are really interested in making sure that these circuits have high reliability, you have to do a global and a local test, a combination of both, which could be 10 delta and partial discharge. That's probably the most common way to do it today. Okay, you can also look at leakage current. Okay, that's if you use the cosine rectangular Vlf unit, you do a withstand test with leakage current, or you can do a monitor withstand test. The monitor withstand test on the other side is really a great, in my opinion, a very great tool to do a commissioning test, because you do a withstand test, you look at that voltage, which is a fairly high voltage, 3 per unit, the highest test voltage that we use. You look at PD level at that voltage level, and you can also see whether you have any leakage. So the PD would be for high resistance defects like voids in splices terminations, and the leakage current tells you whether you have anywhere a low resistance situation typically a mechanical defect from the installation process. So that is really a catch-it-all type of a test, which is described in IEEE 400.2, the monitor withstand test for commissioning a new cable. Is a very, I think, a very powerful tool to do that.
All right, thank you, Jason and Henning. Looks like that is all we have time for today. We apologize if we did not get to all of your questions, but we will be sure to follow up with you offline here in the next couple weeks. Thank you all for attending. We hope to see you again at our next webinar. That's going to be on September 15th at 10 a.m. Central Standard Time. That's titled The Evolution of Insulation Resistance Testing, presented by Jeff Jowett, Megger's Senior Applications Engineer. All right, have a great weekend, and please remember to answer the survey. Thank you.